Welcome back to Elements of Chemistry tutorials. In this chapter, we're going to continue our discussion of nuclear processes, fission and fusion. Fission is the splitting of a nuclei into fragments and particles, releasing energy. The energy produced in nuclear power comes from the release of the binding energy, that force that holds the protons and neutrons together, that strong nuclear force. In this example, we have a nuclear bombardment reaction. So we're having a neutron hitting our target nucleus. So we hit the parent splits into two large fragments. Notice these are not small fragments, these are big chunks. If it's uranium, we're looking at things like barium and krypton. But what's most important is that you're getting three free neutrons. And these neutrons can cause other target nuclei to split into more fission products. And this is what leads to what we call a sustained chain reaction. So these extra neutrons, we have to try a means of controlling them. Okay, so here's a graphic showing you the actual chain reaction process where you have potentially three, because you had three released neutrons, hitting more. So the neutrons are really important. The neutrons have to be moving at just the right speed. If the neutrons are moving too fast, they're going to ricochet off. Too slow, they'll get absorbed in. So those neutrons have to be moving at just the right speed. And for that to happen, you've got to have some way to control or moderate that speed. If you have enough nuclear material in one place, it's called critical mass. This is why chain reactions of fissile material don't wipe out everything on Earth, because we just don't have enough of the right isotopes in the same place at the same time. Okay, so critical mass is really important. Critical mass is having enough fissile material, fissionable material, in one place to sustain that chain reaction. If we don't have enough mass, they call it subcritical mass. Too many neutrons can escape and the reaction will stop. If you have too much supercritical mass, it's going to explode like a nuclear bomb. That's why nuclear power plants don't explode like a bomb. They don't have, oops, I put subcritical, but it's really supercritical. Typo here. They don't have supercritical mass of fissile material. They actually don't have enough stored on site to take care of that. And nuclear power plants are designed in such a way that we control that speed of the neutrons and absorb extra neutrons. To better understand this, let's actually look at the design of most of the nuclear power plants in the US. Okay, so you have a core, that's the fuel elements. We would call that the core or the nuclear pile. In the core where you have the fissile material, you have to have a way of slowing down those neutrons. We call that a moderator. In the US, we use water as our moderator. And you have control rods. These are usually boron and cadmium. If you lower the control rods in, they absorb neutrons and the reaction slows down. You pull the control rods out, the reaction speeds up. The energy released is in the form of heat, which heats up water, which will then turn a turbine. That'll generate your electricity. You'll have a heat exchanger to cool that water back down a bit. And it just makes a system. You always have a pressurizer, something to help take care of extra pressure. We don't want to get up too fast. And you have two completely independent streams of water that don't mix. And that's an important one. So why did Chernobyl explode? We've all heard about Chernobyl. That was a nuclear power plant in 1986 that exploded. Well, they had a different design than the US plant. Here in the US, we use water to slow down the neutrons. They use graphite. Very effective. But the problem with graphite, it's a form of carbon. It burns. So they were doing a testing what would happen if you pulled all the control rods out. Well, obviously the reaction's going to speed up. They didn't have enough time to drop those control rods in fast enough to absorb those extra neutrons. The reaction got out of control. It produced a lot of heat. It produced a lot of steam, and that graphite began to burn. That steam built up pressure, blew the top off the building, through nuclear core material all the way up into the atmosphere. It traveled the jet stream, and we could actually detect core isotopes across Europe, even into the US. They had problems with it getting into the milk. There's all sorts of things because that dust fell down onto where animals graze. Um, We actually knew they had an accident before the USSR, this former Soviet Union, actually admitted to it. Um, it was a huge problem. There's some really great NOVA videos explaining what happened, the cleanup, what's gone on since 1986, because that whole area nobody could go back to. So Chernobyl's kind of the global problem. They called it a level 7 disaster. So the next question begs, well, what happened in Fukushima? Fukushima is the more recent one. Uh, in this disaster, the reactor was cracked due to a giant earthquake, a 9.0 magnitude earthquake, followed by a 15-meter tsunami. Well, as soon as the earthquake happened, the reactor was shut down. But the problem was the tsunami, the tidal wave, wiped out the cooling system and the core began to melt down. Because of damage to the entire building complex, some core material was released into the atmosphere and into the Pacific Ocean. So building a nuclear power plant in a highly geologically active region probably wasn't the best design, but we put them near water, near oceans, because we need a lot of source of cooling. One of the advantages to that is in Florida, the nuclear power plants, they heat exchange with ocean water, and they've made areas that are thriving sites for manatees to stay warm in the winter. So there are some benefits. So what about the US? Have we had a big disaster? Well, we did have one problem. Back in the 1970s, something called 3 Mile Island, TMI. It was a partial meltdown of one reactor at a complex at 3 Mile Island Nuclear Generating Station in Pennsylvania. It's considered the most serious accident in US history. It was a combination of equipment failures, some design flaws, and human error. Steam from the primary cooling system was released into the atmosphere, but no detectable core material was released. The incident significantly damaged the public trust in nuclear power, and since 3 Mile Island, we've sort of cut back, and a lot of the nuclear power plants are being taken offline when they've served their usefulness, their design usefulness. Um, some are even getting taken down before. But the problem with nuclear power, in this case, fission power, is that waste. That core material is radioactive for tens of thousands of years. And what to do with the waste? We've got to store it somewhere. Um, a lot of people are trying to think about putting it in salt domes because they're very stable geologically. But that is a problem to consider with fission. So a lot of people, that's why they're against it. Even though it doesn't produce greenhouse gases, it doesn't contribute to global warming, there's a lot of other problems with it. So we need to work on that. The goal for the future is this nuclear fusion. Now, if nuclear fusion, where fission meant split, fusion means combine. Instead of splitting and converting the mass defect into energy, fusion takes small, light nuclei, hydrogen, and combine them into a larger nuclei, helium. Hydrogen and helium, both very, very safe. They're not radioactive. This is the energy process that occurs in stars like our own sun. What happens is you've got a couple of isotopes of hydrogen, deuterium and tritium. Deuterium is hydrogen that has a neutron. Tritium is a hydrogen that has two neutrons. Okay. These get fused under intense heat and pressure, basically making a mini sun, into helium, and a neutron is also given off. So, simply put, nuclear fusion is the process where two light nuclei combine to form a single heavier nuclei while releasing massive amounts of energy. Fusion reactions take place in a state of matter called plasma, a hot, charged gas made of positive ions and free-moving electrons that has unique properties distinct from solids, liquids, and gases. To fuse on our sun, nuclei need to collide with each other at very high temperatures, exceeding 10 million degrees Celsius, to enable them to overcome their mutual electric repulsion. Once the nuclei overcome this repulsion, they become within very close range of each other. The attractive nuclear force between them outweighs the electrical repulsion and allows them to fuse. For this to happen, the nuclei must be confined within a small space to increase the chances of collision. In the sun, it's extreme pressure produced by the immense gravity that creates the conditions for fusion to happen. The amount of energy produced from fusion is very, very large, 4 times as much as nuclear fission reactions, and fusion reactions can be the basis for future fusion power reactors. Plans call for first-generation fusion reactors to use a mixture of deuterium and tritium, heavy types isotopes of hydrogen. In theory, just a few grams of these reactants, it's possible to produce a terajoule of energy, which is approximately the energy one person in a developed country needs for over 60 years. This is a quote, I quoted this whole section from the Atomic Institute, and I thought they did a really good job, and I couldn't have phrased it any better. An interesting fact here, all naturally occurring elements except for hydrogen were formed from fusion reactions. So if you've ever looked at MIT OpenCourseWare, there's a really great series on production of the heavier elements. Take a look at it. So fission splits, fusion combines. We have fission reactions happening all the time, and there's power plants all over the US, even here in Texas. But fusion, we can only get it to happen for a very short period of time. That they actually contain in what they call a magnetic bottle. And it takes a lot of energy to get it going. And realize you're looking at tens of millions of degrees Celsius. It's so hot, it'll basically melt just about everything. So there's fission and fusion. Hope this answered your questions. Stay tuned for later videos. And as always, stay curious, be safe, have a wonderful day. And if you have questions, go ahead and put it in the comments.